Hello and welcome. In this video, we're going to be taking a look at AP Physics 1 Review Free Response for Two-Dimensional Kinematics. In other words, projectile motion. Let's take a look. Remember to pause and rewind the video as necessary. Problem number 1. An object of mass m is projected horizontally from the top of a building. The object's initial velocity v and initial height h as it travels a horizontal distance d before striking the ground. Let t represent the time the object is a projectile. And we're given a picture of this up above. Well, when you're dealing with a projectile, you're dealing with the idea that horizontally, we move with constant velocity, and vertically, we move with free fall acceleration due to gravity. Which means these break down the equations we will ultimately be using. Since these deal with 3 variables and these deal with 6 variables, typically a projectile motion problem is going to be a list of 9 total variables. For instance, in the horizontal direction, you would have x, v naught x, and t. In the vertical direction, you would have y, y naught, v naught, and it would actually be vy and v naught y, g, and t again. T is written twice just to remind people that the time it takes to fall is the time it takes to move forward, okay, for a horizontal launch projectile. So it's a good idea to write it twice. Now, the horizontal distance, that would be d. The horizontal velocity would be v, and it remains the same right all the way through. We do not know the time it takes to go this distance, nor do we know the time it takes to fall, and so we're labeled that with an unknown. We're going to leave g. Normally we'd put this as a calculation, we would put g equals 10, but we'll just leave it as g. V naught y is going to be 0 because, as you can see, you're going horizontally. That means you only have x direction velocity. Vy is unknown to us, and that brings us to y and y naught. Well, sometimes it's helpful to make y naught the height of the building, where you're starting from, and y at the bottom equaling 0. Sometimes that's easier to do. You could also let y naught equal 0 and y be negative h, the negative height of the building. It just depends on which reference frame, which perspective you wish to operate from. So with that in mind, part A, write 2 equations that relate the quantities VH, D, and T and fundamental constants. Fundamental constants, they're referring to G. Well, the one equation we could use would be y equals y naught plus v naught yt minus 1/2 gt squared. Okay, y is 0 at the bottom. Y naught is h. Now v naught y is 0, so v naught y times t, well, that would be 0. And then minus gt squared. So if I take all of this and I add it over to the side here, well, I end up with h equals 1/2 gt squared. Similarly, my second equation would be x is equal to v naught x times t, where x is distance d, and v naught x is v. So this really gets written as d is equal to vt. Part B, write a single equation that expresses d in terms of v, h, and fundamental constants and not time. Essentially what it means is substitute for time. So here's what we're thinking. We have h is equal to 1/2 gt squared. Let's solve it for time. In order to solve for time, we have to multiply by 2, divide by g, and square root. So time would be equal to the square root of 2 times h over g. And then we also have that d is equal to v times t. Well, essentially, we're substituting this value for t in place of t. And we would get d is equal to v times the square root of 2h over g. Part C. Suppose the ball is launched a second time with a greater initial velocity. What must the velocity be multiplied in order to double the horizontal landing distance? Well, h is related to time squared. So essentially, if we, well, we don't even need to look at that. We could look at this equation right here. In order to double the horizontal distance, in order to double d, the horizontal distance, the velocity must be multiplied by 2. In other words, 2v, 2d. And you can see this because velocity is directly related to distance that it flies to. So if I double the velocity, the distance doubles. You can also see this because velocity is outside the radical. Double the velocity, double the distance. Part D. Suppose the ball is launched a third time with the initial velocity v, but from a greater height. What must the height be multiplied by in order to double the horizontal distance? Well, in this case, in order to double the distance d, the height h must be 4 times greater. Let's take a look and see why. D is related to the square root of h. So if the h is 4 times greater, well, the square root of 4 is 2, right? And if we're doubling this, we're essentially doubling the distance. Let's see, part E, in terms of the given quantities and fundamental constants, write an expression for the net force of the object while it is acting as a projectile. Explain your reasoning. Well, the net force in the x direction is 0 because A in the x direction is 0. We do not accelerate horizontally. However, the net force in the y direction, well, that's written as net force equals m times A in the y direction. But since A in the y direction is g, the net force in the y direction is just simply going to be rewritten as mg. Part F. In terms of the given quantities and fundamental constants, write an expression for the object's kinetic energy just before striking the ground using your, explain your reasoning. Well, if it wants to know the object's kinetic energy before striking the ground, something flying through the air has a change in speed and a change in height. This is a recipe to recognize that we need to use conservation of energy. It's an energy problem now. And the reason this was shown in here in the problem is because projectiles can be two-dimensional kinematic problems, and they can also be solved using conservation of energy, especially if you're looking for kinetic energy, potential energy, velocity, or height. If you're looking for any one of those four variables, conservation of energy is the way to go. So we have our table here. We have our projectile. And if we're going to use conservation of energy, we need to describe the energies at different points. So at the top here would be the initial energy. And so initially we have initial potential energy, which would be mgh. Should write it differently, mg capital H. Our initial kinetic energy is 1/2 mv squared. Okay. And I don't have to write necessarily v initial because we were told that the velocity off the edge was just v. Okay, and at the bottom, right before it lands, a couple things. One, the final potential energy is 0, because right before it lands, it has no more potential to fall. Gravity has no more potential for gravity to make it fall. Therefore, essentially the lowest point in the problem is potential energy equals 0. And we're looking for kinetic energy final. That's what we're looking for. The object's kinetic energy just before striking the ground. So our equation for conservation of energy problems would be equating the initial and final energies. The initial energy would be mgh plus, right, add it up, plus 1/2 mv squared is equal to kinetic energy final. Now there's our equation. But we have to double check and just make sure we've written it into the proper constant. So let's just double check. So K final equals mgh. I think I'm allowed to use those. Let me just double check. M is a given quantity. G is the fundamental constant, and H. So I'm allowed to use that. Plus 1/2 mv squared. I'm allowed to use m, and v was given as well. So this will work as a final answer. Problem 2. 8 objects are launched horizontally from the top of a building. Some objects have mass m, the others have mass 2m. Some objects are launched with initial speed v, others are launched with initial speed 2v. Some objects are launched from the middle of the building so that they have an initial height h. Some are launched from the top of the building with an initial height 2h. In this one, we want to be able to rank various things. For instance, in part A, we're going to rank the objects based on the time that elapses while they are projectile from the longest to the shortest amount of time. Part B, we're then going to rank them in terms of the horizontal distance they travel before landing from farthest to shortest. Part C, we're going to rank them based on acceleration magnitude while it is a projectile. Part D, we're going to rank them based on net force magnitude while it is a projectile. Let's begin with part A. How do we begin to rank them in terms of time and horizontal distance? Recall the two equations that we're going to need for horizontally launched projectile problems. H is equal to 1/2 gt squared. Solving it for time, time is equal to the square root of 2h over g. Why is this important? Because the time it takes to fly through the air completely depends on height and the acceleration due to gravity. But since all these objects take place near the surface of the Earth, g is irrelevant. In other words, time is proportional to the square root of h. That is the relationship we really care about. And distance that it flies through the air is equal to velocity times time. Right? Or v equals or x equals v naught xt would be the other way to write it. You could always write it like that too. Now, let's use this to rank the times. Okay, so since time depends on height, the ones that are going to have the longest time are going to be the ones dropped from the highest heights. Which ones are dropped from the highest heights? That would be E, F, G, H. And again, I do not care about the velocities being different. Velocity doesn't matter with regards to time. So E, F, G, and H are all equal. And they're all going to be a longer, greater time than A, B, C, and D. Because A, B, C, and D, you can see, are all dropped from height H rather than height 2H. Time is proportional to the square root of H. Pictures E through F are launched from height 2H while pictures A through D are launched from height H. Well, in part B, we now have to rank them a little differently, because if we keep into account that D is equal to V times T, and we put it together like we did in question number 1, problem number 1, then D equals V times T can be written as D is equal to V times the square root of 2H over G. Well, it seems that when you're dealing with distance, you now have to combine velocity and height. The greatest combination of velocity and height will be the greatest distance. So let's take a look at that. The greatest combination of velocity and height would be, well, we have two m. Now m doesn't really seem to matter. The mass doesn't matter yet. Okay, we just want velocity and height. So 2v, 2h, 2v, 2h. Those ones are the greatest. So F and H would have the greatest horizontal distance because that's the greatest combination of velocity and height. Next would be 2H, a combination of either 2H and V or H and 2V. So 2H and V, 2H and V, 2V and H, 2V and H. So in other words, B is greater than B, which is equal to D. Now, which one would be greater? Well, it seems to me that if we take a look at these 2v and 2h, if we double the velocity right here while keeping h constant, then d is going to double. So let's take a look at each one of these using this model right here. Okay, so in object A, you're going with V, speed V, and H. So you're just going to fall distance D. That's just going to be distance D. But this one is falling from height H, but speed 2V. So you're going to be going 2D. Double this, double the distance. Here, we doubled the mass, but everything else stays the same, so you're still going to go distance D here. Object D is just like object B. You're doubling the mass, but that doesn't matter. You're doubling the speed, you double the distance. Keeping the time the same, we're going to go 2D. Okay, for object E, you may be going V, but you're doubling the height. Now, if we double the height, that means it's going to be the square root of 2. The square root of 2 times the distance. So the square root of 2 times the distance is a little bit less than 2 times the distance. Okay, it's going to be about 1.41, I guess, would be the correct way to say it. Object F, we're going 2V and 2H, so that would be a double times 2H, which would be 2 times the square root of 2 times D. This would be V times 2H, so that would be the square root of 2 times D. And this one again would be 2 times the square root of 2 times D. So that might help you rank them just a little bit better. These would, of course, be your number ones right here. These would be your number twos, because 2 is greater than the square root of 2. These would be your number threes. And these would be your number fours. So that seems to probably be the easiest way to rank them. So B and D are greater than E and G, which are greater than A and C. Okay, so again, using distance is equal to V times the square root of H over G. D is based on the combination of velocity and height for each object. Okay, letter C, we're ranking them according to their acceleration. Well, projectiles, I'm going to explain this before I rank it, make it easier. Projectiles only accelerate due to gravity. And that's a constant value. That's G equals negative 9.8 meters per second squared. So if that's a constant, that would tell you that A, B, C, D, E, F, G, and H are all the same. Same magnitude of acceleration. Okay, now, a net force in the y direction is equal to mg. G might be constant, but m was not constant. Now is where we have to factor in the mass. So projectiles C, D, G, and H. Let's look at that. C, D, G, and H all have twice the mass. They're twice the mass. And therefore have twice the net force. So we would rank them C, D, G, and H over A, B, E, and F, which are all mass M. Okay, suppose the value of V is such that V is equal to the square root of 2GH. This would make it so object A starts with equal potential and kinetic energies. A bar graph for object A is shown below for the instant just after it is launched. Let's complete the bar graphs for B, C, D, E, F, G, H. Well, in this instance right here, the final kinetic energy, now keep in mind, the final kinetic energy of these is going to be based on the sum of these two. Because as we remember, the final kinetic energy was the initial kinetic energy plus the potential energy. So in this one, I'm going to make some notes here. The final kinetic energy is going to be 2 units here because this is 1 unit plus 1 unit. Now, for object B, let's take a look at what's going on in object B. Object B, we're moving twice the distance. What's the kinetic energy going to be like? We're focusing on kinetic and potential energy, mind you. Well, we're going for height h, so since it's height h, that means and it's m, so it's mgh, it's going to be 1 unit of potential energy. One unit of potential energy, but then the kinetic energy is going to be a little different. See, the kinetic energy is twice the speed. So since kinetic energy is proportional to v squared, and potential energy is proportional to, well, it's proportional to 2 things. It's proportional to, if it's equal to mgh, it's proportional to 2 things. It's proportional to mass, proportional to h. So this is m, and then 2v squared. So m times 2v squared, the kinetic energy, would be 1 mass unit times 2 velocity units squared, which would be 4. Okay, my potential energy, on the other hand, is just equal to equal to mgh, but it's proportional to mh. So we have essentially 1 mass unit and 1 height unit for a potential energy of 1. Okay, and object A had 1 for everything since everything starts with 1 unit. Okay, so we're going to do 4 kinetic energy units. Okay, which means the final kinetic energy is going to have 5 units of final kinetic energy because we have 4 plus 1, right, to give you 5. Now what about object C? All right, well, object C has a potential energy proportional to, again, mh. So we have 2 mass units, so 2 mass units and 1 height unit. So we have a potential energy of 2. And kinetic energy kinetic energy is proportional to mv squared. So we have 2 mass units and 1 velocity unit squared. 1 squared is 1 times 2 is 2. So both of these have 2 units. So I'm going to go to my bar graph, and I'm going to 2 units of kinetic energy, 2 units of potential energy, and the final would be, of course, 2 plus 2, or 4 units of final kinetic energy. Again, total energy remains constant, right? So the initial energy has to equal the final energy. Let's look at object D. Object D, let's see, potential energy is equal to M, proportional to mH. So that would be 2 mass units, 1 height unit for a potential energy of 2. The kinetic energy is proportional to mv squared, so that would be proportional to 2 mass units and 2 velocity units. But you're going to square the 2 velocity units, so 2 squared is 4, times 2 is 8. We have 8 kinetic energy units. So we have 8 kinetic energy units, 2 potential energy units. The graph changes dramatically now. We got this and this. Okay, which would tell us that we would have 10 final kinetic energy units, right? Because we got to add those. Let's look at object E. Object E, the potential energy, again, is proportional to mH. So we have 1 mass unit. Looks like we have 2 height units for a potential energy of 2. So it's twice the potential energy as object A. And kinetic energy is proportional to mv squared. So we have, looks like 1 mass unit and 1 velocity unit. Okay, so we have a kinetic energy of 1. So potential energy of 2, kinetic energy of 1. And the final kinetic energy would be the sum of those 2, or 3 units total. Let's look at object F. Let's see, object F would have potential energy proportional to mH, which has 1 mass unit, 2 height units. For the potential energy is 2 times greater than object A. Kinetic energy is proportional to mv squared. We have 1 mass unit with 2 velocity units. 2 squared is 4, times 1 is 4. So we have 4 kinetic energy units, 2 potential energy units. Two and 4. For a total of 6 energy units. 6 kinetic energy units when we add up those two. Let's look at object G. Object G, we're going to have a potential energy, again, proportional to mH, would be 2 mass units and 2 height units. So now we have a proportion, our potential energy is 4 times greater than the original object A. Kinetic energy is proportional to mv squared, which is 2 mass units and 1 velocity unit, for a kinetic energy of 2 units. So we have 2 and 4. And the final kinetic energy would be 6 units, right? The sum of those two. And lastly, object H. Let's take a look at object H. Okay, now object H, potential energy equal to mH, which has 2 mass units and 2 height units, which means we're 4 times greater potential energy than object A. Kinetic energy is proportional to mv squared. We have 2 mass units and 2 velocity units squared. 2 squared is 4, times 2 again is 8 kinetic energy units. We're going to 8 and 4 this time. 8 and 4. And the final kinetic energy would, of course, be 12, right, when we add those two. Okay, so we just did part E. We filled out the remaining bar graphs. Now what we're going to do is we're going to rank them based on their kinetic energy right before striking the ground, which is why I found the kinetic energies afterwards. So we can clearly see that H has the greatest kinetic energy at 12 units, followed closely by D, followed closely by F, but F and G are the same. They're both 6 units. Followed by B. That seems to be followed by C. Then E. Then A. In that order. Okay, and again, kinetic energy final is the sum of kinetic energy initial and potential energy according to the law of conservation of energy. Lastly, rank the objects based on their speed before they strike the ground. Think about how the final kinetic energy can be used to solve for the final speed. Okay, let's take a look at that one. So the final kinetic energy would be 1/2 mv final squared. That was equal to mv squared plus mgh. Let's solve this for v. We're going to multiply everything by 2. We're going to divide by mass. And when we do that, we're going to square root. When we do that, we get v is equal to v squared, v final rather, is equal to v squared plus 2gh. And again, you can see v is independent of mass. So that doesn't seem to matter with the final speed. What we will be looking at is v is proportional to the square root of v squared plus h. That's really all I care about. Okay, v squared plus h. That's the proportionality I'm going to be looking at. So let's do them one at a time. V sub a is proportional to, okay, now I'm looking at my v squared. So object A, 1 and 1. So it has 1 velocity unit plus 1 height unit, right? We get about the square root of 2. B, now for B, we have 2 velocity units, 1 height unit. So 2 squared plus 1 would be 4 plus 1, square root of 5. The velocity is c. I've got 1 velocity unit, 1 height unit. 1 squared plus 1 would be, again, the square root of 2. And the velocity of d is proportional to 2 velocity units, 1 height unit. Two velocity units, 1 height unit, again, square root of 5. Continuing on with this analysis, the velocity of E is proportional to, let's look at graph E. Picture E has 1 velocity unit, 2 height units. So 1 velocity unit plus 2 height units. 1 squared is 1 plus 2 is 3, square root of 3. Velocity at F. Looking at picture F, you can see we have 2 velocity units and 2 height units. 2 squared and 2. Well, 2 squared is 4, plus another 2 is 6. The velocity at G, let's look at picture G. That has 1 velocity unit and 2 height units. 1 velocity unit and 2 height units. 1 squared plus 2 would be the square root of 3 again. And finally, H has 2 velocity units, 2 height units. Which again gives us a square root of 6. So doing this, we can see which ones are going to give us the greatest speed upon landing. Well, F and H come out number 1, which would be greater than B and D, which would be greater than E and G, which would be greater than A and C. In problem 3, it says, on another planet, an experiment is performed in order to determine the acceleration due to gravity at the surface. A platform that can be adjusted to different heights and set on the horizontal ground, a ramp is attached to the top of the platform. The lower end of the ramp has a flat section as shown. First, multiple trials are done to show that if a ball is released from rest from the top of the ramp, the speed of the ball at the bottom of the ramp is about 1.26 meters per second. The height from the bottom of the ramp is adjusted to the 5 values shown in the data table. For each height h, the ball is then released from rest and becomes a projectile at the bottom of the ramp. Horizontal distance d that the ball travels as a projectile is recorded. Now, something to consider here. If we're talking about good old conservation of energy, if we are releasing the ball from mgh and it gets down here at 1/2 mv squared, and mgh equals 1/2 mv squared, solving for v is the square root of 2gh. Since this height never changes, this speed will be constant the entire experiment. So let's just make a note of that. This is going to be constant for all trials. What's going to differ is we're going to change the height from the table that it's launched from, which changes the time in the air and thus changes the distance. Remember, time, right, was proportional to the square root of h, okay? But we'll get to that later. First part says, what quantities must be plotted in order to yield a straight line for the graph? Explain your reasoning, fill in those quantities on the right table above. Ladies and gentlemen, this is an example of another type of lab-based question. This is a lab-based data processing question. In a lab-based data processing question, you're usually going to be asked to graph certain things. You're usually going to be asked to linearize certain concepts. This is a perfect example of that. Since you are accelerating due to gravity here, if you were to plot horizontal distance and height, well, let's just say we can start with the following. Distance equals velocity times the square root of 2h over g. Now, what you can see here is that distance is proportional to the square root of h, because remember, this is a constant, this is a constant, this is a constant. In other words, the graph would yield a square root function, not a linear function. So how do we begin to linearize this? Well, here's what we do. Start with the main equation. D equals V times the square root of 2h over g. The first thing I'm going to want to do is get rid of that radical. Okay, so I'm going to write it again. D is equal to V times the square root of 2h over g. I am going to square both sides. And I get d squared is equal to v squared times, now the square and the square root cancel, so the 2h over g just pops out. Now what I want to do is I want to go and analyze each one of these as being a variable or a constant. Now this is really easy to figure out, ladies and gentlemen. A variable would be what you measured. A constant would not. Did I measure distance? Yes, that makes distance a variable. Did I measure velocity? No, I did not. That was a constant value of 1.26 meters per second off the edge of the table. That's a constant. So if v is a constant, v squared will be a constant. 2 is obviously a constant. And g, the acceleration due to gravity on this planet, even though it's what we're looking for, still a constant value. H would be the other variable mentioned. What we then do is we take this and we're going to write it as a ratio of rise over run. That's the important part. We need to rewrite this. Now, how do we do that? Well, I've got my rise right there. My run, I can divide by h, and I get d squared over h. D squared is my rise, h is my run. D squared in meters squared versus h in meters. And what would that be equal to? Well, what's left over here? 2v squared over g. And what is rise over run, ladies and gentlemen? It is your slope. Okay, so slope is ultimately going to be equal to 2 times this velocity over g. How do I find g? Swap those. G is going to end up being 2 times the velocity squared over your slope. So let's go ahead and find the slope. Now, before we do this, let's fill in the quantities in the right. So what do I need to do? The x variable is still going to be height. It's still going to be height in meters. So I'm going to just copy that down as if it didn't change. The y variable, on the other hand, is going to be d squared. So I got to take all these values here and I got to square them. So 1.02 squared, well, that's about 1.04. 1.41 squared, that's close to 2, about 1.99. 1.72 squared is close to 3, that's 2.96. 1.98 squared is really close to 4, that's 3.92 squared. And 2.22 squared is fairly close to 5, it's 4.93. Okay, we're going to be plotting these ones, and you can see the scale would go on the x-axis from 0 to 2.5, and from 0 to 5 on the y-axis. Let's make our scales. 0, 1, 2, 3, 4, 5, and then we would probably go 1, 2, 3, 4, 5. So I'm thinking 0.51, 1.52, 2.5. There we go. Just move this out of the way there. That makes that 0.0. And so these would obviously be 0.25, 0.75, 1.25, 1.75, and so on. Let's plot. The first one we're going to plot is we're going to go over a half, up a little over 1. Over a half, up a little more than 1. So our first plot point is about right there. The second one, we're going to go over 1 and up 1.99, so almost 2. Right there. Whoopsie. The third one, we're going to go over 1.5 and up 2.96. Almost 3. The fourth one, we're going to go over 2, up 3.92, so almost 4. You can see how linearized this is getting, yeah? And lastly, we're going to go over 2.5 and up 4.93, so up almost 5. We're going to draw a best fit line through this. Like that. And then what we're going to do is we're going to proceed to find the slope. The slope on this one looks approximately from here to here. It seems to almost go through the corner of those boxes. Pretty close anyway. So this would be a rise of 1, a run of 0.5. So a rise of 1 and a run of 0.5. Okay, and we plotted over here, so we did part B. We're now working on part C, which means use the slope. So first thing I'm going to do is find the slope. The slope is approximately, let's see, 1 over 0.5. It's approximately 2. And so if we use the relationship of 2v squared over g equals your slope, switch those out, g would be equal to 2v squared over this slope. And the slope, ladies and gentlemen, represents a graphical average of your data points. Not a numerical average, but a graphical one. So 2 times 1.26 was that constant launch speed squared over approximately 2. That nicely cancels, and you take the square of 1.26, we get roughly about 1.59 meters per second squared. Now, the nice part about doing problems like this is you get a flexible range of acceptable values for finding slope. So you just want to make sure you're finding it as accurate as you possibly can be. Remember, there are partial points that you're trying to get in problems like this. So you're not going to get exactly the same number I have, but it should be fairly close if your graph looks fairly close to mine. Again, this is the AP Physics 1 projectile motion in 2D free response review.